Fuentes, who I'm sure you all know and love. And it is simply impossible to, okay, I'll let you. To properly introduce her. Former department head over at NC colleges of Virginia. Great, excellent. So,
no, thank you. Thank you for the presentation. Disclaimer, she's my former postdoc. Thank you, Elizabeth. Good afternoon. It's wonderful being back here in North Carolina, and I would like to thank the organizers for the opportunity to be here with you today. And I think that this presentation is going to complement very well what you have seen in this environmental health session, because we have already discussed some of the main challenges in being able to make inference about the impact of environmental stressors on human health. And some of the main challenges is to be able to characterize properly the exposure across time and space while carrying the different sources of uncertainty in the characterization of the exposure, and how to combine the effect of different sources of environmental stressors. And that's really the focus of this presentation. To be able to introduce the statistical framework, I'm going to go into a little bit more depth into that framework in the context of an application of interest. So here we are working with a particular health outcome that in many cases tends to be a little more neglected. We tend to see much more work with mortality, morbidity. So here I'm going to be focusing on pregnancy outcomes. More specifically on birth defects that also we tend to neglect more. We see more work with gestational age and birth weight, but actually birth defects are the major cause of infant mortality, and that's one of the reasons why we are focusing on this particular type of outcome. The incident rate is 3%, and among the different defects that we have, there are abnormalities that are present at the time of birth. The orofacial birth defects are the most common ones, and those are the ones that we are studying now. So they occur when this particular type of birth defects, they are malformations in the mouth, really. So what happens is that the tissue doesn't join properly then in the lip or the palate, and as a result, we end with some openings. So when it happens in the lip, that's called cleft lip. When it's in the palate, then it's the cleft palate. So those are the birth defects that we are working on here. Again, they are the primary cause of infant mortality, and even those children, if throughout the rest of their lives, they probably are going to be much more likely to develop different type of diseases. From an economic perspective, we spend every year $2.7 billion just on the hospital costs associated to these birth defects. In the literature, what we have is relatively limited in the context of pregnancy outcomes. We have been looking at gestational age, birth weight, and some work has been done with birth defects. And there is an understanding or some expectation that environmental exposure are somehow related to these birth defects. The reality is that only in 30% of the cases we know the cause of the birth defects. So in those cases, what we know is environmental or genetic. So what we are trying to do here to explore a little bit more the environmental health relationships in the context of this particular outcome. So right away, yes, the challenges and one of the reasons why we don't see so much work on this type of problems is the difficulty, as you have heard before today in the other two sessions, in characterizing the exposure. So we have the pregnant population. We need to link that to, in this case, we are going to be working with pollution. So we need to be able to interpolate or somehow have the pollution at a given location at a given time. Pregnancies are complicated because you don't know really when during the pregnancy. Maybe it's a little the time that is more susceptible. So that's part of what we want to do, to understand the windows during the pregnancy that will be more impactful in the context of leading to this adverse pregnancy outcome. On parallel, in the context of the spatial aspect, throughout the pregnancy, maybe there is mobility, and that's one of the challenges for the most part. If the data, if we have spatial information, we tend to know what is the residence of the mother at the time of delivery, but maybe it was not the location where the mother was during the pregnancy, which it does happen. It's not uncommon for pregnant women to move during the pregnancy, in particular to end in more urban areas at the end of the pregnancy. So all that, brings challenges, and in the context of what we know right now about these birth defects is limited. There are a few studies linking these outcomes to few birth defects, few different type of pollutants, and the data are aggregated, so we don't really have a very good understanding of the impact, except for we do expect to have some type of association. These particular birth defects, the math is being formed around the 4th to 7th week during the pregnancy, so it's very, very early on, which makes it a little bit more difficult to be able to establish the linkage. So with regard to the characterization of the exposure across the space, so for the most part, what we tend to see in this type of studies is trying to link the location of the mother, in this case, to the closest monitoring station. That can be challenging in many cases when we are working with some of the pollutants of interest, as right now the particulate matter, which is small particles floating in the atmosphere. In those particles, the composition changes across the space and time. So it's important that we look also at the composition, because the risk could be different if we are exposed to sulfur versus nitrates. There's very limited information that we have about those particles, the composition across the space and time. So it's limited data, so maybe we tend to aggregate across the space. So it's difficult to provide this exposure characterization. So putting it all together, these are the challenges that they are very common to other environmental health problems. And just highlighting them here, and I'm going to introduce a framework that I believe can address all of them. So the first one is the spatial aspect, to be able to make an assessment of the linkage between the exposure to pollution and this adverse pregnancy outcome across the space using geographic information that we have for the mothers. But in doing so, the challenge is to be able to properly characterize the pollution with limited data across space and time. The other aspect, which is, I would say, one of the main challenges that we have right now, is the multi-pollutant or multi-exposure characterization. And I hope that there is maybe some work group that is formed to address that important problem. So we work with that here. We are going to be putting together multi-pollutants, very highly correlated, with the purpose of being able to still make inference about the impact that jointly would have on the pregnancy outcomes. And it's also multiple responses that we are working with. We are interested in making inference across the space, but also across time, which is critical with these pregnancy outcomes. We are interested in what particular week or time during the pregnancy the exposure to pollution was much more impactful, while being able to characterize all different sources of uncertainty. So those are the challenges that we have, and we'll be introducing a framework to address all of them. So let me talk a little bit about the application. This type of data is not easy, as you can imagine, to obtain. So let me elaborate a little bit more on the study that we are part of that allow us to get access to these health outcomes. So this is part of the National Birth Defects Center study. And there are 9, this is funded by CDC, and there are 9 states in the United States, part of it. So we are working with California data, one of the main states. In California, California represents itself already 15% of the births that we have in the United States. And every year, about 17,000 of those have birth defects, and 2,000 of those children don't quite make it to their first year. So as part of this study, by state law, we are allowed to track those women and invite them to be part of this study. So we have 8 counties in the central part of California. They are a part of this study. Those mothers have agreed to participate, and we have quite a lot of information about them. On Parallel, what's being done is from the birth certificates that we have, randomly select a group of controls. So this is the data that we have, 200. So for this time window from 2003 to 2006, we have about 200 cases and a little bit over 300 controls. Throughout the pregnancy, we are following these women, so we have the mobility. So we do know what the residence would be at any given time, and that data is being geocoded. So that would allow us to make proper inference about the exposure rather than relying, as has been done in other studies, on what is the information at the time of delivering. So we have geocoded the data, and about 15% of those women, they move throughout the pregnancy, and when they move, they tend to move, as I mentioned it before, to more urban areas. We also have the clinical estimate with regard to the day of conception, and that's quite relevant for us because we are very interested in what happens very early in the pregnancy. So it's important that we have reliable estimates of the beginning of the pregnancy. So that's the information that we have with regard to the health data and also covariates. I'll show you first the geographic here. So what you see is the residents. We have ads and noise to protect the identity of these individuals. But this is in California. The majority are in the central part of the state. But we follow them so they could still continue the study even if they move to other parts of the state. And then what I'm showing is location of the monitoring data that we have. We are combining data from different sources, and this framework that I'll be introduced shortly would allow us to combine different sources of data with potentially different sources of error, which is, again, one of the challenges in this type of environmental health problems. So you can see the location of the monitoring stations, I was told not to move. Let me go back here. Sorry. So we have the two different stations. These are air quality stations, Improve and SDN. They use different type of instrumentation, and they are in different areas. The Improve is more rural, SDN is more urban, so they have very different characteristics. And then here we have with the in gray the residence of the mothers. Okay, so the information that we are using with regard to the mothers, we age, the baseline here is going to be under 20. Pre-diabetes, they have diabetes prior to the pregnancy, education, job status, to high blood pressure, the sex of the infant. And we also have smoking and alcohol, but that's self-reported, so it does not tend to be very reliable when we work with pregnant women. So this is just a little bit of breakdown of the information that we have. It's not uncommon to have both types of birth defects, lip and palate. So you see it here in the table, the numbers that we have for each one of these categories of just exclusively one, exclusively the other, both of them, and this is the number of control cases that we have. So this is the breakdown of the data. The health data. So let's talk a little bit about the air pollution data. You have heard a little bit more about air pollution. So this is a follow-up to what you already heard about challenges working with the PM 2.5. So the PM 2.5 is a pollutant that is being regulated, small particles. So the reason why it's of great interest to us is because, well, first of all, it hasn't been really studied in the context of birth defects. And then secondly, because by being so small, those particles, they can penetrate very easily. They can get to the placenta, and that can lead to different type of changes or inflammation in the placenta that is expected to lead to some of these type of birth defects. So that's the goal, to be able to work with the PM 2.5. Challenges with the PM 2.5 is that the PM 2.5, we regulate it based on the mass. So a PM 2.5 means something really different depending on where you are. And that obviously should have a great impact when we're talking about health effects. It really doesn't make a lot of sense to just look at, just mass. You want to understand the risk is expected to be different, potentially if you're being more exposed to carbon, nitrate, sulfate. So that's one of the challenges working with the PM 2.5, but we do have access to those components. So then it becomes a multi-pollutant problem because we are going to be working with the components of the PM2.5 or what we call a speciated PM2.5. So in California, we do have a number of stations that will report, in some cases, daily, every 3 days, every 6 days. It really depends. Those stations provide data collected by EPA or by the state, and we combine that together. And as I said, the stations are different, and it's important that we characterize that in our model in the context of the type of measurement error, or even just what would be expected, the mean of what the behavior would be at those stations is expected to be different. So these are the main contributors to the PM2.5, or the main components, the ones that explain the majority of the mass, and those are the ones that we are working here with. And some of them are very different, or they are expected to correspond to very different sources. In other cases, they are very similar, so there is higher correlation. And these are the locations throughout the state that we are working with. So we have in blue the improved, that corresponds to more rural areas, and again in black SCN that corresponds more to the urban areas. So the behavior changes across time as is expected when we work with weather, air pollution. So this is a little bit more the temporal cycle for the different components in the study. And we have combined together the two different monitoring networks, one in black, the other one in red, at the different locations, and the vertical bars are to separate years. So you can see a clear yearly cycle and different type of behavior depending on the pollutant. So the point I'm trying to make is that the temporal aspect is obviously very important too. So in working with this multi-pollutant problem, one of the things that we need to be careful is how we bring this information into a statistical framework when they are highly correlated in some cases. So all that you see here is what is the correlation across these different components. So in some cases, it's as high as 0.97. In some cases, it's as low as 0.01. So they are different pollutants. They have different sources. So one of the main challenges, and that's why we tend to avoid it for the most part in these environmental health problems, you work with a pollutant at a time, or you try to, maybe two that are orthogonal. So that's what we are trying to address here, how we can together put all this information that we have in the model. Okay, so let's go into the statistical framework to be able to address that. So this is going to be implemented into a Bayesian framework, very computationally efficient. The reason to go that direction is because the different sources of uncertainty that we have, and we are going to be breaking this framework into smaller conditional models that would not only offer computational benefits, but would make much easier to bring together a lot of different sources of information. So first I'm going to talk a little bit more about the exposure characterization that, as I explained at the beginning, I believe that this is one of the main challenges when we work in environmental health problems, and this is going to be integrated into the health model. So let's talk about the pollutants. So we do have, in this case, the components of the speciated PM2.5, and that's what we call here Y, that changes across time, that changes across space. So that's why S of T, and we have different pollutants, so that's the sub-index P. So they are correlated potentially, as we have seen. What we are going to introduce here is really a dimension reduction approach that can lead to orthogonal components that can be used into the health model. So essentially, that's what it is. The challenge here is because the spatial-temporal aspect of it. So a way to think about it, what we are trying to do is we are working with these pollutants, and we're trying to identify the sources of the pollutants. So when we talk here about sulfate, nitre, carbon, so we could have different type of sources. Could be traffic, it could be different factories. So there are different type of sources generating, those pollutant concentrations, and that's really what we would call factors. So in this case, delta. So here we have the pollution, and there are different sources that are generating those pollutants. And at the end of the day, that's really why we care, right? In the context of regulation, we don't quite regulate in many cases the sources, but really that's where it's coming from, and that's what would lead different characteristics, right, into the pollution. So what we're trying to do is to identify those sources, and it's expected that if traffic is is one of them. Well, traffic changes across time, so that's one thing that we had to keep in mind. So that factor is going to change across time. I mean, it's going to change across the space too. But the relationship between traffic or the fraction of the nitrate, that could be one of the components, the fraction of the nitrate that is explained by traffic, it could be different depending on where you are, right? So, so it's expected that the loading, so these coefficients for the factors could change with the space. That could make that a little more challenging. So we have the factors that change across the space and time, and these are going to be the loadings, the weight, or how much of that pollutant is being explained by a given factor. So this is, the basic concept here. And then what we allow is those factors to change across time, and that change could be different depending on where you are. And here you could have still a spatial residual component. So this is really a state space model. And you have an observational model here, an evolution model. You can call it in different ways, but what we're doing here essentially is reduce the dimensionality of the components by identifying these factors that they change across the space, they change across time. The evolution, the propagation is also space dependent, and then these weights also are expected to change across space. Yep. This lambda is not fixed. It's gonna be spatial. There are some constraints that we have for lambda to make this identifiable, but we are gonna put to this lambda a spatial prior, so it's gonna become a spatial process. Yeah. Yeah, so so it would be all the same. These are the way we model. These would be with these would be the latent processes. It can be the coefficients of the bases. It would be really all the same thing. These are unobservable processes, and these are going to be spatial processes. So this is the latent process that evolves across time. But let me just maybe I'll put in the next slide a little more information about the structure for those lambdas, because the first thing too is the identifiability. There is a lot going on here, right? A lot of latent processes at different levels, but it is identifiable, and we'll go through these. So a few things here with regard to the residual components. So this component in the propagation or the evolution model is going to be allowed to vary spatially and to characterize maybe the residual spatial dependence that we still haven't been able to pick up in this model. Okay, so let's talk about the lambdas here. So for to be able to identify these components, so we are going to impose that they are series. So this is going to be an upper triangular matrix, basically. So so the ones in the lower triangular component, they are going to be 0. In the diagonal, they'll have to be positive. And for the rest, we are going to treat and we are going to put a Gaussian process prior, so they have a spatial covariance to characterize the spatial behavior of the lambdas, because the lambdas themselves, they are going to change across the space. And since this one has to be positive, it's going to be a log normal. So, so that's just this first equation here, the observation equation. So this to establish the structure here of the loadings of these factors. In the context of the next equation here, when we have the evolution, so the sources of pollution are expected to change across time, right? If we are talking about traffic, we would expect that from one day to another, 1 week to another, there will be changes, and those changes could change across space. To make this a stationary process, we are going to put some constraint in these coefficients, so they're going to be between -1 and 1, using a truncated normal, because again, these are changing across the space. So here we are treating that with adding a covariance function that would allow for that spatial dependence here. And then we initialize, so the delta, the factors will be evolving whatever way they have to across time, but we just initialize them here as another spatial process. And then these we are making them orthogonal, so this is going to be diagonal. So I think that you can visualize here the concept. So what we are trying to do is to identify, again, dimension reduction or factor analysis, but it's a series of components that are going to be here orthogonal. This is going to be diagonal, and the weights here are going to be spatial. This is going to change across time, and this will be spatial too. And with this set of constraints here, that will be identifiable. In the context of being able to sample for those from the delta, so the delta, the factors, the orthogonal components that we want to use in our health model, we need to be able to sample or simulate or predict those values at any given location at any given time. And to make that in a computationally efficient manner, we are going to be working with a forward filtering, backward sampling approach that basically just give a step forward and then a step backwards. So you go forward to get to some given end state, given a series of observations, and then you go backwards by finding what will be the probability of the remaining observations just given that state. So that will make it computationally efficient. Another aspect of it is that we are combining different sources of information about our exposure from different places that will have different characteristics. So we can easily add that to the pollutant framework that I have introduced here, because all that we need to do here would be for the different sources of information. In this case, we are working with two very different monitoring stations. We could have satellite data, we could have different type of information. It would be the same type of approach. We would add a different type of error. The error that we have in the model that you have seen would be different depending on the station, and the mean would be different too. So that would be added to the framework that I have introduced already. The different characteristics about the different sources of data. So while everything is going to be fitted together as part of a fully Bayesian approach, I wanted to sort of break it down and talk with a little more time about the pollution. Now I'm going to do about the health model. And again, the pollution now, this is a supervised factor analysis, because it's going to be fitted simultaneously, so the health information actually is going to determine to the factors. So let's talk about now the health outcomes. So we're in a situation where we could have either just one birth defect or the other, or both of them, or none of them. So that's why the way we model here the outcome is two binary responses. So one would be no cleft palate, or yes, that would be the value 1, and the same thing for the other. So we can end in a situation where these both are 1, so we do have both, which is not that uncommon, or we have one or the other. And to be able to make inference, to be able to interpret the results. So what we are going to do is here, this is a probate framework. The reason why we also go this way is for the computational advantages and conjugancy that we gain. But here, to make this interpretable, what we are going to define here is latent continuous real variables here, Z, such that when one of the outcomes is 1, which means that a pregnancy outcome is ending on that birth defect, that latent variable Z is positive. So that's what we have here. So the Z will be continuous, but we're really working here with a binary outcome. So that makes interpretable the coefficients, the model, the health model that we have here. So what we want to do is to be able, again, to make inference about the impact of these multi-pollutants on different environmental stressors on these outcomes of interest. So here we have also some personal characteristics. There are a lot of different confounders, different variables of interest. So we bring them all here together. So we have the individual level covariates that we have for the mothers, and then we have coefficients. And the way this is being built, so that now it's a little bit easier to interpret here the coefficients, because when an increase in this covariant, increase in X, when the beta is positive, that means that leads to an increase in the risk of that birth defect. So it makes more interpretable the coefficients. And now we go to the pollution. So here what we bring back is those orthogonal components, so the factors, of the sources, as I was calling them before. So here they are. They are the ones that are going to be used to predict a potential adverse outcome. So here are the deltas, the factors, they depend on the mother, the location of the mother. Here I depend on time, that would be L, and we have a number of them. And as part of this dimension reduction approach, the expectation is that we end with M of them, where M is less than the number of pollutants that we initially had. Okay, so we have the M factors. We have the time window throughout the pregnancy, where we are more interested in making inference. So here we are looking at week 3 to week 8, because the mouth is being formed, about week 5, between week 4 and week 7. So we look at that time window, and again we look at I would be the mother, and then this would be the residual component. And I'll talk a little bit more about the residual component, because part of what we are doing here too is to characterize the dependence between the multiple outcomes. So we are going to introduce some dependence here. Okay, so let's talk about the coefficients of interest here that allow us to make inference about the impact of pollution on the birth outcomes. So the omegas here, or these weights, they are also changing across time. So what we're going to do is to introduce some shrinkage here across time for those components. So part of what we want to do is in a simultaneous manner to make inference about the impact of different weeks. So alternatively, you can make inference about a given week at a given time, but the signal here is very weak, so you probably are going to benefit, well, we know that you benefit by borrowing information across time. And that's why we are doing that here. So these weights are going to be allowed to change across time, but because of the dependence here, so we are going to introduce an temporal dependence that would allow us to determine what weeks of the pregnancy simultaneously would be more likely to lead to an increase in the risk of particular birth defect. And then, again, as I was mentioning before, so here we are going to allow dependence in the outcome. And that's already characterized with these factors that are being shared by the outcomes. So I think that we already introduced some dependence there, but there could be some residual dependence that will be characterized by this error component. Okay, so that's the framework that we are using. So a spatial-temporal multivariate factor dynamic approach to be able to make inference in these environmental health problems. So a question is that how many of those factors we work with. So here what we are doing is just working with using DIC to determine how many to use in this setting. And it seems that one was sufficient here, which is not maybe terribly surprising. That means that maybe it's just building an index, that really characterize the pollution that we have. So in this case, we are going with one factor. And then in the context of evaluating how powerful this approach would be to be able to classify the defects properly. So we are looking at this diagnostic here. So what we are looking is how the model can be able to characterize properly the different birth defects. So we are looking here at the percent of defects that are correctly identified as defects, which is 92%. Okay, so let's try to make inference with this type of framework. So we're going to look at the impact of these personal characteristics, and then we'll go to the pollution and try to understand the impact of pollution and how that may change across space and time. So what we see here is on the vertical axis, so we see the different covariates of interest, and then we are evaluating the significance of the different parameters, the coefficients. So remember, so in this type of framework, so when it's positive, that leads to an increase in the probability of that birth effect, and when it's negative, a decrease. So what we see is the prediabetes is the one that seems to be the most relevant of these personal characteristics here, very highly significant. So you see the predicted value with a 95% credible interval in both cases for both of the birth defects. So we're looking simultaneously at the lip and the palate with different colors, but in both cases, the prediabetes it seems to be the most relevant one. Also, college education, so college seems to decrease the risk. So this is the one that you have here. And, that's really a proxy for a lot of different things, right? The education itself could lead to maybe being able to have a better understanding, right, of the impact of pollution, but it could lead to different type of living status. But that seems to be relevant. And also age. So all the baseline was 20, under 20, and all the other ages, they seem to be a higher risk than that baseline. Not terribly surprising with smoking and alcohol. As I said, this is self-reported, so it's not very reliable. So it doesn't seem to be, it's positive, but not in a significant manner. As I said, it's not terribly surprising. It's not uncommon for women to not come completely truthful when they're pregnant about smoking habits. And then when we look at what happens over time for the two outcomes of interest, lip and palate. So what we see here through different weeks in the pregnancy, so here what we see is week 6 to be the one with a higher risk of when the exposure to pollution seems to be much more impactful. So if we look at the pollutants, so here what we have is the different pollutants, all the different components that we are working with. And just to show you the different patterns, different behavior across space. In this case, you have seen previously across time. So you can see they are standardized. So you can see in some cases, some pollutants are a little more stable across the space. Others, they just change very rapidly. So that's all that I'm presenting here, that there is some different spatial behavior. That's why characterizing properly all different sources of spatial variability is very important in this framework. So here you have other pollutants with, again, much more variability than the total carbon that was in the previous page. But what I want to show you, this is the one factor. So we just go with a dimension of 1 for the latent factor component. So this is the resulting one, and seems to sort of separate in a way just by looking at the colors here. This evolves over time, so this is at a given time, but to identify some areas here in southern part, California, San Diego, Los Angeles, more the central part, the domain. Here we see San Francisco. This is the eastern part. So it seems to sort of separate areas that we know that are different in the context of the pollution behavior. And then what we also observe that is changing clearly across time here is the loadings, which justifies having in our model not just the factor component factor analysis, but with the spatial varying loadings. And these are the loadings for the different components, and you can see the spatial variability that is different depending on the different speciated components of interest. Okay, so just to wrap it up, so what we have here is a very flexible and very general framework and very computational efficient that it seems to address some of the main challenges that we have in these environmental health problems with regard to be able to properly characterize exposure across space and time, and more importantly, to be able to address the multi-pollutant problem or different sources of pollution or environmental stressors. But I want to finish by also sort of supporting some of the initial evidence about the adverse impact of pollution on these pregnancy outcomes, that we do see some evidence that very early in the pregnancy there is an increased risk of this particular type of birth defects due to the exposure to air pollution. And I hope that this can lead to continue dialogue to be able to continue developing very robust models that can help us to be able to make inference in these really very, very important type of societal problems. Thank you.
Very narrow window for the fetal development of Thank you so much. The very narrow window for the development of cleft palate in the fetus suggests that we probably would see temporal changes in the rate of cleft palate syndrome because pollutants have seasonal components.
So I mean, so that's being characterized. I mean, the seasonality in the behavior of the pollution. I mean, we are characterizing that temporal behavior in the pollutants, and that's why we have the temporal evolution there, and we have also a mean in the model that is temporal too. So the in the pollution model, we do have a spatial-temporal intercept to characterize certainly that temporal behavior. Yeah.
Significantly more cleft palates in winter, for example.
Right. No, I don't believe that. Well, Kimberly, my postdoc, is here. Where is Kimberly? Kimberly, that question is for you. Do you remember seeing?
In California, we didn't necessarily see more in the winter time. It was a little bit more even across where the study period was and kind of when they collected them. But other states, that's more true in them rather than ours.
By the way, she's Kimberly Caulfield. She's in Los Alamos. She's former postdoc working with me, and she's the hardworking person who made it all happen.
So great. That actually gets us right back pretty much on schedule. So let's thank Montse again. And